You just saw me playing the guitar. It is not necessarily related to coroutines, but there may be a relation. We will see that further in the video. What this video is about is coroutines and threads, and it is the second part of a video that I have created before about the basic topics surrounding coroutines and threads. These are two very intrinsic topics to the way they work. In the first video, I discussed things like the release of threads, how coroutines work on threads, and how they differ in terms of runtime and in terms of their execution. I talked about an important topic, and that was the voluntary release of a thread and the gaining of control of a thread, and the way coroutines may or may not regain control of another thread. When we talk about regaining control of the thread or releasing the thread to be used by other coroutines, what we are actually talking about is something called suspend functions. And suspend functions are an integral part of how Kotlin coroutines work. This is because suspend as a keyword has been added to Kotlin, to the language, so that we can make a clear distinction between the blocking code and the reactive code. This is important, and we will see much later on in other videos how does this play a role with frameworks like the Spring framework or Quarkus, for example, or other frameworks like, for example, Ktor. And we will also see in this video how contexts work and how contexts can change the way a coroutine works and how can we pick the different contexts for our runtime. I have mentioned before, and if you've been watching the channel from the beginning, I've talked about coroutine context before. There was this video where I talked about coroutines and tried to make a relation between how they work and real-life objects. The only thing is that I may have expected too much of the viewer from that video, because some of the basics of how coroutine works, for example, that they are not threads, they work on threads, that they are not lightweight threads, they are just lightweight. Those things are also important when watching that video. And I've made all of these different videos, which are shorts, explaining in these short videos things about coroutines very separately. There was one even, a video for about 20 minutes, a 20-minute long video, where I talk about how to predict coroutines as an answer to a quiz. These are all great videos, and I really recommend you watching them. And the other video that I recommend you watching, of course, is the video before this one. Now, the links are all in the description. And there you'll be able to see these videos, and perhaps after watching this one, you may have a better understanding of those videos. If you didn't understand those videos, of course, because I'm sure that many of you have already seen those videos, and many of you perhaps already understand what those videos were about and what were the topics discussed then. But this video is different. This is about going from the basics, slowly learning more and in more detail how coroutines work. And as always, the best way to start learning these topics perhaps is to first look at some code examples and see how this actually works, especially when talking about suspend functions. Because suspend functions is something that we, although not mentioning suspendable or suspend or suspension even, we did work with them. And perhaps you already know one of them that we work with as an example. Let me just say that all the different functions that we use in our example, that we can call and potentially release the control of that thread and come back and regain control, not necessarily to the same thread, but to another one. All of those functions are suspend functions in Kotlin. So perhaps you already know, right? It's sleep. No, it's delay. It's delay. Delay is a suspend function. So, having said that, let's get into the world of delay. In this example, we have seen before what is the difference between coroutines and threads. We've seen with this code, which we have built, that a coroutine will take control of a thread and that it will voluntarily give control back to the thread. But we only did a practical example using delay, and we found out that the whole body of this function will have a total runtime of about 4 seconds. And we also found out that that was because when we are delaying, we aren't doing anything with the thread, so the thread is released so that it can be used by another coroutine. And that way, the total runtime here resulted in the 4 seconds, or roughly 4 seconds, considering the negligible amount of times, which we measured to be around 20, 30 milliseconds, something like that. The one thing that we missed in all of that discussion from the previous video is what actually is behind the delay specifically. Well, delay, if we look inside of it, we can see that delay is marked with this suspend. A delay is effectively a suspend function, and that means that it is a suspendable function. It tells us, the developers, that potentially this function can be suspended. And here in this case, that is what happens. The function gets suspended and it will resume execution later on in the same or in another thread. If I, for example, go here to the companion object and simply create a suspend function where I just simply say report. I call it report, and I simply call here a print line execution time. No, that's almost what I wanted, but let's say that instead of execution time, let's say reported. Just reported. So we want a suspend function that will just print a report. It will just print reported to the console. And now IntelliJ is already saying that this suspend is not necessary, but also that report is not being used. If we look at the comment of IntelliJ, we see that it says that redundant suspend modifier, remove redundant suspend modifier as a suggestion. But we will now use it in this coroutine over here. And we have seen before also, just as a small recap, that when we call run blocking, we are creating a coroutine. Run blocking itself is a coroutine builder, and then we are running a coroutine, which we have seen before that the reason for that is that it has a coroutine scope and there is a coroutine context associated to it. So essentially we found out that a coroutine is simply the runtime combined with the task that is being used, which is the set of instructions that the coroutine is about to execute. But we will call now here the function report as an addition to the body of run blocking. And we find out something interesting. The report function is being used, so IntelliJ does not complain about that, but it does complain about the usage of the suspend keyword. If we, for example, inside this function call a delay of 1 second, IntelliJ will stop complaining and it will assume that this suspend is needed. And that is because before, without the delay, the suspend keyword is unnecessary here. And the reason why it's unnecessary is because just the print line will never be a suspendable instruction. Print line is not something that we can stop in the middle of its runtime. It's not like we can call print line and then just before it prints out the lines of whatever we want to print out to the console, we can just suspend it, do something else, and then come back later. No, that's just an instruction. It runs and that's it. And then we continue running. So although we have marked it is possible to compile this code with the suspend on this function, although we can do that, there is literally no goal there. And this is where we come to the reason why the suspend function might be used. So the suspend modifier in Kotlin doesn't really have a functional purpose. It has the purpose of making the code clearer. In general, the suspend modifier makes it so in our code that we have it very clear what is the boundary between the blocking traditional code and potentially a reactive code, a code that will run with coroutines. If we put suspend on a function, it means that that function can only be called by a coroutine. The function itself, the function marked with suspend, is not a coroutine. And let me just focus on that. If we use suspend function report, this does not mean that we have created a coroutine. It means that we have created a function that can run by a coroutine and only by a coroutine. It is not a coroutine itself. And at the beginning of making this channel, I actually created a video specifically talking about that, this one over here, where I simply just discuss very shortly why a function marked with suspend is not a coroutine per se. And one way to illustrate what I just said is simply to go here at the top of the function where we call this print line, and just before we call run blocking, we try to call this function. If we try to call here report, like this, the compiler will immediately complain that report is a suspend function. And that means that we can only call it via a coroutine. And that also means that if we try to call it via the normal thread, the main thread in this case, it will fail because a suspend function, suspend fun report unit, should be called only from a coroutine or another suspend function. But at the end, the suspend marker has that function. It separates also what we normally do, the traditional code, and a specific bytecode that will be created following a state machine, which will make sure that the coroutines run the way that we want them to run. This is something that the Kotlin X library provides us with, and that way we can use code that is ready to use with Kotlin Coroutines. The Kotlin X library, where we can find the coroutines, also has other functions that we can use that are also suspendable functions, thus functions marked with suspend. And we also have the ability with that library to create our own suspend functions. It doesn't mean that we are always bound to the usage of delay. We can use, for example, something different, which is withContext, for example. It allows us to specify the context, which is something that we will talk about in the second part of this video. But for now, very quickly, I can show you something that is just for illustration purposes. For example, I can start another context with dispatchers unconfined. In here, I can launch other coroutines. But at this point, we now have another context. That means we can use another set of threads that are prepared to run with this context. In this case, I chose unconfined. We will see later what that is. But what's important also is to realize that withContext is also a suspend function. So that means that this suspend function is also suspendable, and we have an indication that we can suspend it. Another thing that we need to be very much aware of is that when we create a suspend function and we mark a function with suspend, it doesn't necessarily mean that that function will suspend. It means that it can potentially suspend. It doesn't mean also that it is a coroutine. It means that it can only be called by a coroutine. So let's now expand our code and see what we can do besides delay. So if we get over to this side of the code, we can create some code to help us understand suspend a bit better. And for that, if we go over here and we create a new coroutine with run blocking, and we launch one coroutine inside of it, and we call some function. Let's just say we're going to say perform task, and we're going to give it a number. And let's say that this is a suspend function. Let's go over here and say suspend function, perform task, IntelliJ says I want times. No, I just want an n because it's the cardinal number of one task. And here I want to do a for up to 5, for example. And then inside, what I want to do is print, and perhaps IntelliJ will use its AI capabilities to help me make a nice log. Not really. So, oh yes, performing task, and let's just say iteration I, except that the task is n. All right. That was not too bad. So we're now performing task, whatever task, in our case task 1, and we are going to perform 5 different iterations. Now, let's not do anything in between and just say finished task n iteration I. That was a good guess from IntelliJ. And in the middle, let's just call yield. And here at the top, let's launch another coroutine and let's perform task 2. This IntelliJ is really good, I have to say. We kind of don't need to type as much, and the guesses are pretty out there. But before we run this example, let me just first comment yield. And instead of yield, let's just put something else, like for example, let's just say performing. And just performing, no need to say which one is it. The idea here is that it does something in between. And notice one important thing. The suspend is still being signaled by IntelliJ that it's not being used at all. As we have seen before, a function like this has no single suspend point. So it will never actually be suspended. So suspend is useless, both in the case for coroutines or just for the blocking code. If we put here suspend, the only thing that means now at this point is just that only coroutines will be able to use it, but we will not expect any suspend to occur. So this function is technically not suspendable, although in the code we can read it as a function that it is suspendable, but it's not suspendable. If we run this code as it is right now, 1 second, let me first remove this code over here, the first part of our tests. So this one is not needed for this experiment. And if I run this now, there's going to be an interesting result. And the result is that the execution of the different coroutines happens almost sequentially. We can see here that the first iteration occurred for task 1. Then immediately afterwards, we can see the second iteration for task 1, third and fourth iterations, and then 5. And then we got 2, 1, 2, 3, 4, 5 for task 2. But these 2 different tasks were supposed to be executed in parallel. Why didn't they do that? One interesting aspect of the code that we are running here is that it runs quite quickly, and the instructions are sent out one after the other. And it is true that they are called as the runtime goes through the code. So that is one aspect of why we see it running sequentially. And another aspect of running this code is that we are launching these 2 coroutines from another coroutine that has been built with the run blocking coroutine builder, which creates a context for us, which is called the blocking event loop. And this means that the coroutines only have one thread to share. And that also contributes to the sequential logs that we have seen by running this coroutine job. But the best visualization is, of course, going to the board and seeing how this actually runs under the hood. So let's have a look at it right now. Let me open the board, and let's start by doing what we did before in the previous video, and that is first we create an axis where we are going to draw our threads. And here we'll say that this is a time axis, and let's just draw two threads. Let's call this worker thread 1, and let's call this worker thread 2. And here, let's just say that this will be the yield example. Now we already know that there are lots of threads running in parallel to these two. Let's put a dotted line here just to represent that there are many of them that are running in parallel and they are available in parallel to use. When we start running our application, we do start one coroutine on one thread. For our example, let's use worker thread 1. And it's going to run up until it needs to launch the first coroutine. Now the first coroutine will launch and it will not call any suspend function. It will just loop through that for. And because it doesn't suspend, it will keep on running. So that means that all through the period of that for loop, these 5 times that it runs through that loop, it will hold and block the thread effectively. It would theoretically not block the thread, but it does so because of this circumstance. And if we then draw coroutine number 2, which is this one, it will do also the 5 times loop. And then, of course, in the end, the run blocking would continue to run until it stops. This is how coroutines work with that example that I showed and ran just now. If we go back to our code and run it differently with yield, we will see something different, which will change radically the way this runtime works, and it will make it rather complicated, but it will also highlight a very good advantage of using non-blocking. So here, because we did not use any single non-blocking call, that means also that there was no suspend point, which is what we get when we use delay. But in this case, there is no delay, there's nothing. And that's also one of the reasons why IntelliJ tells us immediately that suspend doesn't do anything here. It is true, it doesn't do anything functional, that we have already established, but it also means that there is no suspension point. However, if we use yield here, then the two coroutines will call this function. And with that call, they will have the opportunity to switch between each other and use the same thread and share it while they run, and it will give us the effect that they are running in parallel on the same thread. So if I run this now, the different outputs should not be ordered. And they are not, because we can see here that the first line is performing task 1 on the first iteration, and immediately we see that task 2 is also doing that. They are effectively interlaced with each other. One runs, the other runs, the other runs, the other runs. And why does this happen? It's because yield gives back the control of the thread. It releases the control of the thread for one moment to let the next coroutine use that thread, if no other is available. So our graph changed quite radically. So let's go back to it and let's see what happens in the drawing board. So at the first moment, nothing really changes. The run blocking, or the coroutine created by run blocking, runs up to here roughly the same time, and here begins the interesting part. Because they are using yield, they are effectively switching in an orderly way with that for loop. So that means that the first run happens here, then there is a yield over here, and this is just for one iteration. Then what this yield means here is that this one can run, but this one then have another yield, and that means that here we get to print to the console the last line. So one iteration is complete here for the blue task, and then it starts again in the loop. When it starts and finds the new yield, what happens is that our second coroutine will continue to run up until here, completing one loop cycle, but it will continue until it yields again. So there's one yield here, and there is another yield here. And this will happen over and over 5 times until it gets to the end. Now, this has been maximized, so this would continue off the chart, but I think you get the point. That means that all of this will be running in a way where these two coroutines are interlaced with each other. The benefit of this has to do with resource availability. If the first coroutine would continue to use that same thread, then that means that that thread would be constantly occupied, which is what happens over here at the top. We can see that here the same thread has been used, and here the same thread has been used. There's no change. So what happens is that way we are only using 2, perhaps 3 threads over here if we had more threads available. And here, just as long as threads are available, this could have a different shape if we have more threads available. And so that means that if we have more threads in this case, or more threads in this case, not just worker thread 1 or just worker thread 2, this graph would have many different shapes. But the one that would hold much better would be this one over here, because this one can share more threads and the whole runtime doesn't have to use just 3 threads, which is the maximum number of threads that this whole process would use. Just those 3 threads, and have them blocked for so long as they are running. This illustrates another important aspect, and that is that we need to have suspension points to be able to make sense of the use of suspend functions. And another thing that it does, it tells us the reason why we should not and cannot, and why Kotlin X made it clear that we cannot use and establish this constraint where we cannot use suspend functions with blocking code, because suspension points don't make sense in blocking code. If I remove this, although this doesn't do anything, it restricts the usage of yield, because this function this way would never be called in a way where suspension would be expected. And of course, it's debatable if Kotlin X should have or should have not made this restriction. It makes it very clear, however, what code are we running and where it's being used. And just for that reason, it makes perfect sense to use the suspend modifier in our functions. Having said this, there is yet another way to create suspension points. And that other way is to use the suspendCoroutine function. And to understand how a suspendCoroutine works and why does it help us understand a little bit better the dynamics of suspend points, I have created one example for this. And the reason why I created this example, and I'm not going to develop it with you in this video, it's because it would take a substantial amount of time to complete the example. And the idea here is that we understand exactly what a suspendCoroutine function does for us and what it allows us to do. So, for that, let's go into the example and see exactly what it's doing and take conclusions out of it, which will help us understand suspend functions and suspend points. Right here at the bottom, you can see a main function. Oh, and by the way, this example is located in the suspendCoroutine job class that it's also located in the same module that we have seen before in the JE.org Kotlin test drives project. Okay, so if we look at the main function, we will see that the first thing that seems to be what we are trying to do, and it is the calculation of the amount of time it takes to run the whole program. This is important because we are dealing with things that will run synchronously and asynchronously. So in the first part, we measure the time in mils that it takes to run this run blocking. Now we already know that run blocking is a coroutine builder, and we get a coroutine here at this point with a scope and a context. What is also important is that immediately at the start of the coroutine, we are printing the current coroutine thread and the current coroutine context. The same is valid at the end. The idea here is that we understand which threads are we running and what happens to the coroutine context in these cases. Then we make two calls. The first call we make to a myCustomSuspend function with 1 as an argument, and the second one we make a call to the same function, but instead of 1 we use 2 as an argument. This will distinguish the two different calls to this function. What we have over here in this block, this is the body of the function that will be executed by the coroutine, and we at this point only see one coroutine in our code. If we call the myCustomSuspend function, we will get to this point over here at the top, and here we start to see how this will all work and the dynamics of this code. Now, what's important here, the first thing to understand is that we are calling a suspendCoroutine function, and it has as an argument a unit. The idea of unit is to specify the return argument, which in this case it's just unit. We don't want to return anything with this. This is t, this is the one over here. Now, the suspendCoroutine function is an inline function, and for those of you who don't know this, inline means that the function will be compiled into many different versions of it for each call point in our code. And it basically, the goal of it is to try to work around the type erasure. And that is just one of the many ways that inline can be used. But this is not the subject of this video. If you want to know more about inline, I can suggest you to watch this video or this video. They're all very good videos that explain to you how inline works. But we are interested here in suspend, because here we are also calling suspend. That means that here, this is a suspend function, the myCustomSuspend function, which will now call a suspendCoroutine with a generic type of unit, which is our return type. And then here we get a continuation. Now, this continuation is important for us. The continuation is a representation of the coroutine that we are using. However, we don't have here a scope or a context. At this point, we only have access to the continuation. So if we try to put context here, or if we try to do scope or any of that, this itself is nothing. So there is nothing here for us to understand if this is a coroutine or not. But we are in a place where a continuation is running. Now, what this is right over here is a low-level abstraction of what a coroutine is doing. So in here, we are inheriting the coroutine that we get right over here. And it will continue to run here, although here we don't have any access to the context or the scope. We do have access to continuation, which means that there we have access to the context and, I believe, the scope. Let's have a look at that. Continuation, and then scope. No, do we have context? We do have context. You can see already here that we have access to context, but we'll get to that. And then here we Do we get a scope? We don't get the scope. We essentially only have access here to the context. And what's important is that this will run and this will run almost immediately. And what we have here also is a call to a new thread creation. This thread will immediately start running because we are calling start. And then in another thread, this will run. It will print the current thread and the coroutine context, and then there will be a sleep of 1 second, and then there's going to be a printout of what will happen after sleeping. We will see the current thread and the context, and then we are going to resume. And this is where things start to get interesting. We are resuming our continuation. And what happened here at the end of this code block is that the coroutine gets immediately suspended. This is something we don't see, but it is akin to what we saw before with what happens with yield, or with what happens to delay, for example, or even with context. But of course, with context is for the second part of this video. The idea here is that this is akin to a suspend point creation. The idea here is that this is akin. The idea here is that this is akin to the creation of a suspend point, and we will resume that coroutine right over here. Now this is difficult to visualize. I will continue to explain the rest of the code, because then we will go, of course, to our chart and see this in a more visual and in a way that we can understand this a little bit better. So after we resume our continuation, what that means is something interesting. When we resume here, the continuation will continue to go. But where was the continuation suspended? It's suspended here, right? At the end of the whole code block. So what happens is that when the resume occurs, the continuation can continue. That means that the coroutine can continue to the other call. So these two will effectively run in parallel. This call to number 2 and this call right over here to another sleep. That means that while we are calling suspend function number 2 on the same thread that we called my custom suspend function number 1, another thread will continue and then we'll print out this, while number 2 is already here at this point, calling yet another thread. So this means that in total at this point we've got 3 different threads. One that it is blocked because of the coroutine, and we also have another phenomenon. The other phenomenon is that the continuation is blocked, but it is also blocking the coroutine that is running here. So we are blocked at this point here before running the sprint, and this coroutine will only be released after this resume. The resume here is akin to having the coroutine regain control of the thread. In the examples before, we did not see any explicit call to a code where a coroutine would resume, but in fact, this is what happens behind the scenes. Under the hood, the coroutine resumes, and it will resume in a way that it will look for the next available thread of its designated pool, which is determined by its coroutine context, and it will then run on that thread. At the end, there will be this other sleep, but the program will continue very quickly and it will finish. And this will measure, in my prediction, how much would it measure? Would it measure 1, 2, 3, 4 seconds? 1, 2, 3, or 4. Remember, in the first time, it will run for 1 second, of course, because it will run the first thread. Then it will resume and run this one at the same time as the second call occurs, and then it will try to sleep for 1 second, but at the end the program finishes. So how long would this run? I'm saying about 2 seconds. Let's see if that's true. So if I run it, if you guess 2 seconds, you are right. This is not the easiest thing to understand. I grant you that. But let's look at this in more detail, because if you didn't catch up yet about what is happening, it's important that we have a look again, but now via the logs. And if we go through the logs, we will see a couple of things that will strike us immediately when we read it. If we go to the first line and we see the logs and we highlight the first thread, we will see that it is shared all across the logs in the output, where I have mentioned that the thread is shared, the main thread. So if we go here to start, we can see that the worker is 1.5. Then we see here 1.5, then we see here 1.5. We see that it happens before suspension 1. So what that means is that the code ran from here, then it called this function. By calling it, it is calling also the suspend coroutine, and the suspend coroutine will have the same thread while printing this and while printing this, which will happen almost instantly. The context is Dispatchers.Default, and the reason why it's Dispatchers.Default is because we specified here that we are running with Dispatchers.Default. However, when we are using Dispatchers.Default, we should be able to access other threads. So why is this so predictable? The reason why this is predictable is because we are not using a coroutine that has asynchronous capabilities at this point. We are simply calling this, the suspend coroutine, and although we would be able to send other coroutines here in a parallel way, this is not what happens with the suspend coroutine. The suspend coroutine will continue to run this coroutine and will allow us to suspend the current coroutine, so nothing will be able to run in parallel, although they are all using the Dispatchers.Default. So if I highlight again the same thread, I will see that the same thread is used when the suspension 2 gets called, and of course the following, when the coroutine gets suspended and when it finishes off right over here at the end. What we don't see is one interesting log line, and that is no, we don't see this. No. No. But this, of course, is the main thread. So the main thread will run this block over here, and it will also run this block over here and this block over here. The different threads will come up here after running this thread. And if I look for this doing something in our and if I look for this something in our logs, I will see it right over here doing something, and I see that the number of this thread is 35, not 32. So it is a new thread, and we can see also that the dispatchers that are associated to it are the default dispatchers as well. So this means that we are in a new thread, but we are still in the same pool of threads, which is also the same what happens after sleeping. So after sleeping, this log over here, after 1 second, then we still have the same. And after that, we will resume our coroutine, and then this thread will sleep for 1 second. And at that time, that's when we get the call to my custom suspend function 2 because it was holding up here. Now it's free to run this. The other thread is now sleeping for 1 second, and that means that the next following line that we get after sleeping is the before suspension 1, where the main thread is running, and then it ends with the coroutine suspended. And at this point, when we get the coroutine suspended, it will print out doing something with a new thread. This will be thread 41, and it will sleep for 1 second. And while it sleeps for 1 second, the other thread that is running, this one over here, will finish for call number 1. And then the code will continue, and you will find after sleeping for call number 2, and again with the dispatcher's default. Finally, we can see also that this simple output never came up for call number 2. And the reason for that is that the program ends earlier. Right here, where it then logs end with the current thread and the coroutine context. Had we waited here for, let's say, let's wait for 2 seconds just to be sure. If we run this now, then we should see as a last log line, the last log line of call number 2, which is exactly what we have here. So we gave it enough time to complete in parallel with this current thread. Okay, so this is this bit of code. However, this is still just one side over our running code, and it still may be a bit difficult to visualize for some of you. And for that reason, let's go into the drawing board, where I will try to design a schema that will represent this code that we have just seen running and that I've just explained to you. Let's go. Our code is very simple, but it does have some complexities to it. So it may be easier for you to first open this project in your own machine and follow the code as I will explain things now in our chart. Here, the first thing that we should do, of course, is, like before, we create our axis. And here we've got one time axis over here, and then we've got our main thread, our worker thread, and let's just give it a name here. Let's call it main. We've got 2 other threads, and for now, let me just draw them. And let's call these worker thread 1 for the suspend coroutine 1 and worker thread 2 for the suspend coroutine 2. And they will, of course, keep going in this direction. When we start our code, we start with a run blocking, and this starts here in main up until this point over here, let's say, and here it will print out the start. Here it makes the call to the suspend coroutine 1, and the first thing it does is a logout to a before suspend. Then at this point right over here, it makes a call to another thread. So let's say to thread 1, because we are talking about the suspend coroutine number 1. It makes the call, and now what happens is that it keeps going until it logs coroutine suspended. While at the same time, this one logs the start of doing something, and then it will sleep for about 1 second. So let's say that this around here is 1 second. The coroutine is suspended, so nothing is happening. Over here, there is a call to resume. When this one resumes, then run blocking runs. What this means is that run blocking will run here. That coroutine, the coroutine created with the run blocking coroutine builder, will now start running from this point onwards. And at the same time, the thread running on worker thread 1 is still going to run more. There's going to be a log or a printout, and then it will sleep for another 1 second. Let's say that 1 second is this. This is another 1 second. This one is now running, but now it will make a call to the second coroutine suspend function, or the second suspend coroutine. Coroutine suspend. As it does this, it will still do the before, and then it will do the coroutine suspend. And here in the middle is going to be another interesting thing. Of course, in the middle there's been a call to another thread. This is thread 2, where exactly the same as here above occurs. So here there's going to be a log, just like the one here, start, and then there will be a sleep of another second. This one is suspended, so nothing is happening in this runtime. It's waiting for this 1 second to be gone. And so the run blocking coroutine will resume from this point onwards. And when it resumes, it almost instantly finishes, because this is going to be the end, and the whole runtime finishes off here. This one was sleeping for 1 second, and it would finish off right over here, making this a total potentially of 3 seconds. However, it was abruptly ended because the runtime finished off here. Therefore, the other thread that was running here, this thread here, doesn't continue, and the whole thing stops. That's why instead of 3 seconds, we've got a total of just around 2 seconds of runtime. So this is kind of how it looks. The worker thread 1 finished before worker thread 2, worker thread 2 didn't finish completely, and the worker thread main finished the execution up until the end. So this should have helped you, I hope, to understand what happened here. But in all of this graph, where would you think that the suspend points were? Because we've got one point where the coroutine gets suspended, and we've got another point where the coroutine resumes. So to represent that, I'll use purple. And so if you think that the suspend point is where the coroutine has suspended, then you are correct. The coroutine suspends here and here. So there are 2 different suspend points. That make sure that the coroutine gets suspended. And the reason why the code doesn't continue running, it's because it needs to be resumed. And that occurs with the help of the two different threads that will release this coroutine for every time it gets blocked with the call to suspend coroutine. All right, so this is something about suspend that I wanted to share with you. The other thing is with context. Now, with context is very different, and it's a different concept. If we go to our code and we go to the code that we were busy with in the beginning, which is the coroutine job, we can specify here with context in different ways. But we are not going to do that. Instead, we are having a look at two different examples that I created for you. In the first example, we are going to see where to apply the default dispatchers. And in the second example, we are going to see where to apply the input-output dispatchers. But before we delve into these two examples, let's bear in mind that the default dispatcher is used for CPU-bound operations. It is dependent on the number of cores of your machine, and it has a limited number of threads. And the reason for this specific thread pool that is available for the coroutines that we are going to use on them is because CPU operations normally do not need as many threads as, for example, input-output operations. Those are operations that will benefit from using a context like with the input-output dispatchers. And the input-output dispatchers allow us to use coroutines on threads in the order of 50 to 100 to even more coroutines. The input-output operations are usually things like accessing a file, calling a REST endpoint, opening WebSockets, using WebSockets. Any kind of input-output operation that you can think of is something that should be used with an input-output context. And of course, we are calling context and we are calling this dispatchers. They are kind of the same thing. A context is defined as dispatchers dot something in Kotlin, and that is how we tell our code which dispatcher we want to use. So let's first look at the first example, which is called Dispatchers.Default Job. I gave it this name because when we want to specify which dispatcher we want to use, we use the values that are contained in the dispatchers object. And if we go inside of it and see what it contains, we will find not only the default dispatcher, but we will also find the main dispatcher, which has a slightly different subtype, the main coroutine dispatcher, which is also a coroutine dispatcher. Then we also find the unconfined dispatcher. And then here at the bottom, we will also find the input-output dispatcher. These two are the ones we are going to use, the input-output dispatcher and the default. These other two, main and unconfined, are subjects for the next video, because the next video we will go into the details of how dispatchers work and what these contexts actually mean when we use them. For now, we are just briefly looking at the way these two dispatchers work. So if we go back to our example, we will see that our example is based on pure math. And the reason for that is because we are calculating prime numbers. We are specifying two different ranges. These ones over here, it goes from 1 million to 1,050,000. Range 2 goes from 1,051,000 to 1,100,000. And then we are calling two different tasks using this function, find primes in range, but instead of using launch, we are using async. And async is something new that will also be discussed in the next video, but to put it very simply, it does the same as launch. However, launch does not keep the return value. Instead, it just keeps the information of the running coroutine. With async, though, we can access the return value, and that is because the returned object from async is a deferred, and on a deferred we can apply await, and this await will give us the return value of this function, of these two different calls per variable that we create. When we go up here and find what find primes in range does, we see that it gets the range as an input parameter, and then from then onwards it filters it by the isPrime function. And in the isPrime function you will find a pretty standard way of calculating prime numbers. And we can see that if the number is smaller than 1, it returns false, and then it goes through the whole numbers until the number itself to find out if there is any other number that can divide fully the number received as an input parameter. And in that case, if none is found, then it returns true, because then we are in the presence of a prime number. And if we go a bit above this function, we will see that we've got this yield here. This yield is key here, because yield is what we have seen before, yields the control of the thread. It gives up the control of the thread, and it will later pick up a new one or the same one. So that means that it can wait for the current thread, or it can just pick the next one. And we will see now an interesting phenomenon, because we will compare the runtime of this code the way it is and with just removing yield, and see what the results are in the two different cases. As you have seen, and you have just noticed that in the meantime, I have just added this line over here where we are printing the current thread, and then we are also printing the current context. In the current context, we shouldn't expect a lot of changes, because we are running, and I hope you have seen this before, that when we start, the context that we are using is Dispatchers.Default in run blocking. So this means that we are starting one single thread that will create one coroutine that will run on a default context. How many threads do you think this is going to use when we run this program? That's an interesting question, right? Is it 1, 2, 3, or so many that we cannot count? Or is it fairly unpredictable how many threads is this going to use, regardless of knowing how many cores this machine actually has? All right, let's just run the code and see what happens. It's not going to be one single thread, I can tell you that. Let's run this code now, and let's run it from this point here and see what happens. So it just calculated 6 different prime numbers. And if we now see the full length of these logs, we will see that there is one worker thread here. It seems to be the same all the time, but as we can see, it has also used 2.5, 11.5, 6.5, 14.5, 11.5. So it has used many different threads, and it was fairly difficult to predict how many threads would this actually use, but it has used many different threads while running. And this is because when we use yield, we are indeed returning the control of the thread so that any other coroutine can pick it up, but we are not saying that this coroutine will wait. It will just try and pick up the next available thread. And that is what we see happening over here in this code, where they keep switching. So what would happen if we not use yield? How many threads would this use? This one is predictable, and that is the first clue and the only clue that I can give you before we start running this code. Let's see what happens if I run it now without yield. Remember, we have 2 ranges. 2, right? Let's see what happens. There, so at the end we see already somewhat the same phenomenon that we have seen before. Lots of different runtimes with different coroutines, but with the same thread and with the same Dispatchers.Default context. But we see that we've got here default dispatcher worker 2.5 main. Seems to be the same. Well, there is the 3.5 main, and if we keep going up, we will see no other than 2.5 main and 3.5 main. There are only 2 threads being used, plus the one with run blocking. So essentially we've got 2 different coroutines being launched with async and one coroutine being launched from run blocking. It doesn't sound like an efficient system. To see the difference in terms of runtime of the two of them, we would have to perhaps perform calculations with longer running and more intensive tasks. But did you notice that I did not use any with context, as I mentioned that I was going to use in this example? If you did, congratulations. And if you didn't, now you know. I did not use a with context here. What I did, I started run blocking with the default dispatchers. So what we can do here, and this happens in real life, is that you may want to, for example, in the beginning, use a different kind of dispatcher. Let's just put it, for the sake of experiment, a dispatcher IO here. It's not ideal and it's not what we should use in this case, but let's say we do this because somewhere around here we are making calls to a REST service. And it is important for us to run these calls under the dispatcher's IO context. What we can do here is use with context and specify that these coroutines launched inside this block will then run with the context that we tell it to run with. This will make our code run under this context. And that means that we will reap the benefits of using the default dispatchers with mathematical operations. Let's first make a test of running this code without with context. So I will just comment it out. And now if we run this, we should expect the same switching thread behavior, except that we are not doing that in the context of the default dispatchers, instead in the context of input-output dispatchers. And that is exactly what we see already here. We can see that here everything ran with the context of the dispatcher's IO. And here we see exactly the same phenomenon of switching between different threads. But of course, we do not want to use dispatcher's IO. We want to use the default dispatchers. So for that, let's just go here with context, like this. And let's now run this and see what happens. Now we've got that everything ran with the default dispatchers. Here we have in this side dispatchers default. And we see that the same switching of tasks and of threads occurs on the same scale and with the same kind of opportunity when the coroutines run through it. And in this case, we still have only 3 coroutines, the one that we start with run blocking and the other 2 that we start with the async function. This should give you one idea of what with context does. We see that it switches context, which is exactly what the name of the function indicates, with context. And one important thing about with context is that it is a suspend function. We've talked about this before in this video. But now the important thing is to realize that just as with yield, just as with delay, just as with context, or even with the suspend coroutine, we are creating a suspend point here. We may get the coroutine blocked, which is what we saw with suspend coroutine, or with delay, or we may just simply continue to run with yield, or in this case with context. With context, if we change the context, we are guaranteed to continue to run immediately after switching context and switching the thread pool that it's available to us. So let's now look at the last example where we can briefly understand what dispatchers IO are and should be used for. Let's go there. The name of the example is in the same way called IO dispatcher's job. And again, dispatchers because dispatchers is how we get our dispatcher. .io because the constant that we are using now is IO, which is this one over here. And we can see also that it is a default IO scheduler. It is slightly different. This scheduler is here because, under many other reasons, and we will see this in depth in the next video, this is because it needs to run many threads, and really many threads, more than the CPUs can offer. But that is another story. That's not for now. For now, let's just see the way this code is built. We are just simply writing two parts to two different files in this code, and this code is as simple as saying that we've got two files. We write the first part of that file, then we yield, and then we write the second part of that file with the same thread or with the other available thread. And we are using Dispatchers.io to perform this operation. So it starts right over here at the top in the main function. And here we see that we create two different final variables, file 1 and file 2. And then we create two different jobs. And then we launch these two different jobs with launch. And then we join them because we want to wait until they are finished, because they are just going to write to a file and we don't want to get anything back from this launch. Otherwise, we would have used async. If we go to write to file with yield, we can see that it starts building a context. You probably noticed that the run blocking here doesn't have any specific context. So it should start with the blocking event loop, right? And so it starts here running with the blocking event loop, and then here it will switch the context to Dispatchers.io, which is the one we want and need to run these files. Again, we've seen before that Dispatchers.io runs perfectly. The problem is that in this case, if we would run this code with the default dispatchers and we would have more coroutines running for the typical input-output operations, we would run the risk of facing a thread exhaustion much sooner than using this dispatcher. That's the reason why we have to make that distinction, the basic reason why we make that distinction, but it's not the only reason we make that distinction. Again, here we are just looking very superficially about how and where this Dispatchers.io is supposed to be used. So we continue here, and then at the middle of it, we just wrote part 1 over here at the top. We declared Dispatchers.io, and now we are just logging something. We are saying that the file has been written, and then we yield. And then here we will start another part of the task that will then write the second part to the file. And here we print the current thread that this task is busy with. When we run this code, we should see that there will be a different thread after yield than before yield, or the same thread. Let's add that log before because it's not here yet. So let's just put it here. Now we've got one line before and one line after. Let's also put here before, and then here, let's say after. Let's put it like this, small correction. And now we've got our log perfect so that we can interpret the outputs that this program will give us after running it. So let's just first run this code and see what happens. We have just run the code. We see that before ran on thread 33, which has this name. It's not a default dispatcher, it's just the name of the thread. The actual current context is Dispatchers.io. The second time, after yielding, it will write the second file, and that's why we see here before current thread in another thread with a different number. And then we can see here that we've got after current thread with the same worker as before, and then we've got here the thread for the second file that then uses a totally different thread. This would be thread 34. So that means we've used in total 3 threads. It doesn't necessarily mean that we are always using 3 threads. It can be more. In this case, I think it would be up to 4 threads, if I'm not mistaken, and then it will then print out, wrote second part to file 1 and then second part to file 2. And what's important here also to understand is that in all cases, the dispatcher used was the Dispatcher.io, the input-output dispatcher. We have reached the end of this video. Let's recap what we have learned so far. In the first part of this video, we have gone into the depths of what a suspend function is and how and what does it has to offer. We have learned several things about it, and we have learned 6 points that we should now be aware when using suspend function. A suspend function establishes boundaries between non-blocking code and blocking code. We have seen that only non-blocking code can use suspend functions, and blocking code is not allowed to use them. Using suspend functions allows us to read the code more easily and understand what the intent of the code is. When we are using suspend on a function, we already know that that function is intended to be used by coroutines, whether it is a function that contains suspension points or it does not contain suspension points. We know that that function will only be used by coroutines and it will never be able to be called by a blocking code. Among many things that coroutines have to offer, one of them that we didn't talk about yet is structured concurrency. Structured concurrency is important because it's a concept that allows us to manage coroutines more efficiently, especially if they are establishing a hierarchy between them. This is a difficult topic that we will also discuss in a future video, but not now at this moment. Just get the idea that structured concurrency is something that a suspend function allows us to implement very well in a much more readable way. Using suspend allows us to use functions in a way that they get compiled in our code in the JVM like a state machine. A state machine is something that is an integral part of how coroutines, or in any case continuations, work. Continuations are a part of how Java virtual threads work and how Kotlin coroutines work. Behind them, we've got concepts like, for example, the parking of a continuation, the parking of a coroutine or a virtual thread. These are things that are interlaced with each other and they have lots of things in common. I explored all of this in an article I did a while ago called Good Story, where I've investigated the difference and similarities between Java virtual threads and Kotlin coroutines. This is something that the suspend function and suspend functions in general are key for the generation of the bytecode that will allow this to happen in the JVM. Suspend is not a JVM restriction. Suspend is something intrinsically related to Kotlin X. It is related to Kotlin, but Kotlin X is the library of Kotlin coroutines that allows us to use suspend. But in the JVM, everything gets compiled in a way so that suspend functions work in a way that the suspend points work and that coroutines can access them and run with them. Finally, there are a series of important patterns that use suspend functions in the Kotlin coroutines world. And so in this realm, under these different constraints and different algorithms and different patterns, it is important to use suspend functions. A suspend function is something that is very important also in reactive applications. I've mentioned that here and there in this video, but what's important is that we realize that if we are going to use an application that is reactive and supports Kotlin coroutines, we are going eventually to have to use suspend functions. And therefore, to understand suspend function is crucial so that we implement good applications that are efficient and work well. And if you are interested in that, I do have a video, this one over here, where I investigated the different ways to implement different endpoints, like for example, a get, a put, a post, and a patch endpoint in a REST application using webflogs with Kotlin coroutines in a Spring application. It's called the Spot-On application and it is divided in 3 different episodes that I recommend you watching them. I will put the links in the description below, including the link to the article Good Story on my website. We have also seen in this video two different cases of two different contexts. We had a look at the default dispatcher and the input-output dispatcher. And we have learned that the default dispatcher is important when performing mathematical operations or operations that do not use any external things like input-output access. So for example, if we are just performing calculations and we do have some suspend points there, it's probably interesting for us to consider using a default dispatcher. For the input-output dispatchers, then another consideration needs to be made if we are thinking about using them. Then we use those for cases when we are trying to use input-output operations. Like for example, as we have seen in our example, accessing a file, but it could be for much more than that, and usually for calls to REST endpoints via web clients, for example. So it is important for input-output operations, and we also know that the reason why is it so, it also has to do with the limitations of the default dispatchers, which are limited to the number of cores available to run them. Finally, one very important aspect of what we've learned so far, we have made a distinction between what is a coroutine and what is a suspend function. So remember, just because you put a suspend on it, it does not mean that you have created a coroutine. You have created a function to be run by a coroutine, but you have not created a coroutine yet. Alright everyone, thank you so much for watching this video. Congratulations for reaching this point of the video. I hope you've enjoyed it and I hope you've learned something from it, and I hope you now have more knowledge and information about how to run coroutines, what they are, and what they mean. There is a lot more to talk about them, and we will see a lot about coroutines in the coming videos. Be sure to subscribe to this channel to not miss out on the coming videos. Give us a like. Make sure to leave a comment in the comment section. I would love to hear your comments. Make sure to keep going at the quizzes. Make sure to answer questions there and leave your comments there. I've been enjoying a lot your comments in the quizzes. I believe that you are having a lot of fun with the quizzes. I see that I've been receiving great comments and great discussions in those quizzes. Make sure to keep doing that. Make sure to keep participating. It only helps the channel. And until the next video, stay tech, keep programming, be kind, and have a good one. As a short disclaimer, I'd like to mention that I'm not associated or affiliated with any of the brands eventually shown, displayed, or mentioned in this video.